Okay, I'm going to continue from where we were going through here in chapter 6 of the Floyd book. I have a couple of... thank you. And I better put on my glasses so that I can see this here too. So I'm one of these folks that I could read without my glasses, but I can't see that there. And, I've got to see all the smiling faces. I'm thinking that we probably need to move this class back to 8 o'clock, simply because, the rest of the students are here, they're getting the rooms open on time, and I have another class at 10:15, which means that if I get any kind of break in between, if I start at 8:30, I'm going to cut this class really short. So starting next Tuesday, we're going to be meeting at 8 o'clock, So spread that word to your friends who are not here yet. I hate to do that, but unfortunately, that's just the way it is. I've got 18 hours of classes until this course is finished, so I've got a very full load. Matter of fact, I have class till 7 o'clock at night on Monday night, so even getting here till 8 o'clock is going to push me a little bit. That's all right. Okay, what I want to look at here, and I have not made my mind up on whether we're going to do a lab on this on Thursday. I hope to, but watch your emails for that discussion, or there'll be a sign there. Okay, what the discussion that we were on here, I was going through some of this, and I don't expect you to be able to read the book here, but the last thing we were talking about was the multiplexer. And I'm going to keep these slides in the background here, but I'm going to actually use OneNote for my discussion here, because I don't expect you to read the book, and I want to go through several examples here. But to get back to what a multiplexer does, and what I'm going to do is I'm going to pull this off. We've got here, and I'm going to show it on the bottom of the screen. I'm going to show 3 lines coming in. Select 0, select 1, select 2 right there. So we have 3 lines coming in, and this particular one we have 8 lines going out, or coming in from this end here. And I'm going to call this I0, I1, I2, I3, I4, I5, I6, I7, right there. And we have one output going out right here, Y, right there. And this is the basic demultiplexer. We talked about it last time, your multiplexer. And what this does is, if S is equal to, say, 0, 1, 1, the number 3, then Y is equal to I3. That's just an example of what we're looking at right there. So all it does is it takes one of these and connects it to the output. And it allows us to have, in this particular case, 8 inputs and 1 output, and we can select which of the 8 inputs goes to the output. And what I'm going to talk about here a little bit today is using this in order to do Boolean algebra, right there. There are 2 ways of doing this. The simplest way is fairly obvious, is that we take our truth table, and I'm just going to do a truth table, A, B, C, right here. And here's my output X, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And we randomly, like I've been doing all along, I just randomly put 0s and 1s on the output. It doesn't matter what our function is. Let me just pick one that's a common one Let's use what they call a majority voting. We have 3 yeses. As long as there's 2 1s or more, we're going to put the output as a 1. there's less than that, well, I'll put 0, so 0, 0, 0, 1, 0, 1, 1, 1. So this is a problem called a majority voting, that if more than the majority is equal to a 1, the output is a 1. And it's a kind of a common problem that. So I just picked that one there. Now this is fairly straightforward, is that if we take A, B, and C, and we tie A to S2, B to S1, and C to S0, right there. So we're using our 3 inputs as our select lines, and we take our 8 inputs, and I'm just going to show them here, right here, and no, right here. I've got I0, and I'm just going to say 1, 2, 3, 4, 5, 6, 7, I7 right there. Those are our inputs. And we tie them to either VCC and ground in order to get our desired output. Because remember, the way that this works is that whatever input is selected, that's what's passed on to Y. So in this particular case, we're going to ground, and I'm just going to show a ground line going down here. And we're going to have another line here that's going to go to VCC right there. And we're just going to ground 0, ground 1, ground 2, tie 3 to VCC, tie 4 to ground, and tie the rest of these to VCC. So we've now implemented a 3-input Boolean function using a 3-to-1 multiplexer. It's a very straightforward, and I'm making sure I go through this because as I was looking at final exams from the last couple of years, this question was definitely on that, so that's there. Now the next one I'm going to be talking about is a little bit more complex. That's there. And this one is one that I prefer. We're using the same device right there. We're going to be using the same device here, but we're going to use it in such a way that we're going to do a 4-input. That's there. And let's just kind of go through it by example right here. A, B, C, D, and let me put some rule lines here so I can try to stay straight. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. Hopefully I have enough lines here. 0, 0, 1, 1, 0, 1, 0, 0. I don't think I do. 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. Okay. There's that there, and here's X right there. So we're going to do the same type of thing here. We're just going to pick, well actually in this case I'm just going to pick random 0s and 1s. That's there. And this is not right. I messed this up right there. This is definitely messed up because I shouldn't have 2 zeros in a row. So when I did this, let me start this all over again. We can tell that. Let me try this again here. 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0. All right, that looks better, doesn't it? That's there. Okay. That's there. Okay, now actually, to be honest with you, I did not pick those at random. I picked them in a certain pattern to demonstrate a few things here. Now, what I want to do in this particular case, I'm going to use the same device, and I'm going to tie A, B, and C to my selects. And this is an important problem because as I said, this was on the last three finals, which kind of indicates that I need to put it on this final. This is something that Sheffield says that they want you to know how to do. That's it. So it's one of those little tricks there. And what I'm going to do here, again, I'm going to tie A to S2. This is 2. B to S1. And C to S0. Now, D is not used here. However, I'm going to tie to each of my inputs, I0 through I7, right there. I'm going to tie that to one of four things. In my last example, I tied it to either VCC and ground, and I just tied it there. What I'm going to be tying it to is going to be VCC, ground, D, or D not, right there. And when I look at I0 is selected when A, B, C are all 0, right? So that's these two right there. Does everyone see where I'm pointing that out there? Right there. Right there. So as you look at those, if you look at the top two lines, or those two top lines, A, B, C are all 3 0, right? No place else in the table is A, B, C 0. Right there. So that means that when I put A, B, C as 0, I'm going to use this input right here. Right there. Well, what do I want this input to be on the output? Right here. X. I want it to be, when D is 0, I want it to be 0. When D is 1, I want it to be 1, right? So I want it to be the same as D. So I tie that input to D. When I look at Y1, right here, and where's my color select? Oh, here's my color select. I'm going to pick probably some ugly colors, but right there, that's not a good choice, but right there. But you can see that's 0, 0, 1, right? ABC is 0, 0, 1. That's there. In that particular case, I want the output to be 0 in either case, right? So in that case, I tie that to ground right there. The next case is I2. I2 is going to be these two right here. In that particular case, when we look at I2, we want the output to be 1 in both cases. So we tie that to VCC right there. I3, we look at I3, that's the 3 right here. In that particular case, the output is the opposite of D. When D is 0, I want my output to be 1. When D is 1, I want my output to be 0. So I tie this input to D naught right there. And I go through and finish that out for the rest of there. But you can see a pattern there is that I can have with an 8 to 1 mux, which has 3 select lines. I can do a 4 input Boolean expression with the addition of a single inverter. I need the inverter to do that. So this is a very simple way of getting that there. So let's just go ahead and finish this one here. The next one is going to be here, and that's I4. I4 looks like it's VCC, because again, these are both 1. I5 is this group here. That's going to be D. Excuse me, yeah, D. I6 is going to be these two right here. And that's going to also be D. No, that's going to be D naught. And I7, and my drawing is horrible looking there, it's going to be VCC. Right there. So that's essentially the way that you would do this. So far this morning we've covered 2 techniques of using the multiplexer to do Boolean expressions. One is using just VCC and ground to do a 3-input Boolean expression using an 8 to 1 mux, or using a 3 to 1 mux and a single inverter to do a 4-input Boolean expression. No need for Karnoff maps, no need for sorting through Boolean algebra, just plug it in and go with it. Right there. And this is typically the way that PLDs do it, by the way. Right there. So I just wanted to get that through, and of all lectures, the last 20 minutes are very critical because, as I said, as I look at all the finals, that they all had at least one of these problems on it, which means that if history is prediction, you most likely will see this question there. So I wanted to make sure it was covered very clearly right there. So with that said, I'm going to go back to the notes and kind of go through the rest of these components, but I wanted to cover this topic while everybody was fresh. Unfortunately, some of you weren't here yet at that point, so you probably have to go back and watch the recording for that there. So, and for those who did arrive late, I made the announcement that I'm going to be starting next week meeting at 8 o'clock instead of 8:30. And the reason is I have a 10 o'clock class right after this, and if I want to take a little bit of a break and move to the next classroom, I want to. Matter of fact, we'll probably finish a little bit early. So let's kind of go back to that there. Now, again, we covered that material. This is in the Floyd book, and I did put the Floyd book up on the e-learning, right? Everyone's got a copy of that, or can look at it. So on page 338 covers that first technique that I talked about, and then on page 339 it covers the other technique that I talked about right there. They reverse the A, B, C, and D. If you look at they call their inputs A3 through A0, and see they use A0 here, and then the inverter to go down and pick which ones right there. So this technique is covered in the Floyd book. I don't think it's in the Tochi book. That's there. So it's covered right there. So, all right, as we go through the next one, we talked a little bit about a decoder And a decoder is a relatively straightforward device. But first off, I guess we talk about the demultiplexer right here. Reverses the process right there. And a demultiplexer, what it does is it has a data input and then it selects one of the outputs to pass that to right there. So as we look at the demultiplexer right there, they do it with a timing pattern right there. But what we've got in that particular case, we have 3 select lines, S0, S1, S2 right there. We have coming out of this 8 lines right there. Now depending on the demultiplexer, most of them will take the unselected lines to high impedance, some will take them high right there. And then we have our input Y, that's our input here, and this will be passed to whichever one that we select to right there. Now the advantage of when we talk about a multiplexer and a demultiplexer, the whole concept is based on sharing a single line and having multiple devices on each end that there, and we share those right there. So we have a multiplexer on this end, and I'm not going to necessarily show all the connections right there. We have a demultiplexer on this end right here. We have a single line going in between the two of them, and we have our 3 select lines that are run through a clock right there that will be connected together. Actually, these would all be connected together right here, or synchronized through some type of clock right there. So we would have a clock that would go from 000 to F111 and repeat, so that we grab this one, pass it to here, send it to here. Grab this one, pass it to here. And we share this common line in between. This approach has been used in the early 1900s for telephone switches. I think I mentioned that before, where you have telephone switches, when you make a phone call, typically switch at about 8,000 times a second, right there. It's a signal that is sampled and transmitted to the other end. So telephone switches have about an 8K sampling rate, right there. Now a little bit more of an advanced topic in digital, but it is discussed at this level, is whenever we sample a digital signal, we have to low-pass filter the signal to at least half of the sampling rate. So telephone quality is low-pass filtered to about 3 kilohertz right there. And the reason it's low-pass filtered down to 3 kilohertz, anything above 4 kilohertz is going to create noise. It's going to cause what they call aliasing. Now, telephone switches are using analog multiplexers, not digital multiplexers, but they work the same way. Now, modern phone switches are using digital, right there, but the old style use analog multiplexers, and a lot of the phone switches are actually using fiber from point to point, and they carry thousands and thousands of phone calls on a single serial connection through fiber that multiplexes through. But it's still sampling at about 8 kilohertz right there. Now, has anybody ever made a phone call and talked to a brother or a sister of the person you're calling and not know who you're talking to? But in person, you can tell the two apart very easily. Right there. I got the story of my ex-wife and her sister. They both sound exactly the same. They both have the very rude way of talking on the phone. They're neither, and that's not the reason she's an ex. There's other reasons, but they both have this tendency of, you pick up the phone and it's no assalamu alaikum or hello, how are you? It's like, where are you? So I was living in Malaysia at the time, and I was driving between Banjar and Kajang, where I was teaching a unit 10, and I remember picking up the phone, my phone rings, and I get the, where are you? I'm about ready to get off the highway at Kajak. Okay, did you drop Mom off? Yes. Click, the phone hangs up. That there. As I said, neither of them are warm, friendly people. That there. 30 seconds later, the phone rings again. Where are you? Did you drop Mom off? Yes. And then it's like, hold on, who are you? Didn't we just have this conversation 30 seconds ago? And it turned out that it was my sister-in-law called me first, and my wife called me second. That's there. But I could not tell the two of them apart. Face to face, I can always tell the two of them apart. That's there. Not because they look different, but you can put them behind a screen, and that is because to recognize speech that there and know what someone's saying, you don't need the information above 3 kilohertz. When we look at audio sampling and losing information, there's information there, but to recognize a person's voice, you can come pretty close most of the time with the signal bandpass limited. When I say bandpass, simply means that when we look at frequency in this direction here, and we look at amplitude in this direction, when we look at telephone speech at 3 kilohertz, it starts going down right there. So everything above 3 kilohertz is lost right there. It's filtered out. We don't hear it. Right there. At your age, most of you can hear between 20 hertz and 20 kilohertz right there. So everything between 3 kilohertz and 20 kilohertz, that there, you don't need to know what someone's saying. That there. Now you would need that to hear the idiosyncrasies of the voice, that there. And if you have two siblings that sound similar to each other, but they don't sound exactly the same, you may lose the information that helps you recognize one sister from another or a brother from a brother, especially if they have the same speech patterns and same that there. Now, when we come to something like music, then of course that range is important because that's where you hear, things such as a flute would be above 3 kilohertz. If we tried playing a flute over a phone, most likely it's not going to sound very good. That's there. So when we look at CD quality, CD quality is sampled at 44 kilohertz. And it's low pass filtered down to 20 kilohertz, which happens to be the range of the human ear. Right there. Now as we get older, the human ear tends to hear less and less. Right there. I'm probably down to about 16 kilohertz is my maximum frequency. Right there. Some creatures can hear higher frequencies. Dogs can hear up to like 40 or 50 kilohertz. I know it's not popular in Malaysia. You don't have dog whistles because most Malays don't have dogs for pets. My Chinese next door neighbor does. I'd like to shoot the dog, but that's beside the point. It's a little barking creature that I want to strangle at times. But they sell little whistles that have very high pitch that humans can't hear, but the dog can hear it. Right there. So when we look at our multiplexer right there, right here, where's our last circuit that I just drew right here? That there, I know that I drew it someplace. Oh well, I lost that page. Okay, that the whole idea is that we save a lot of wiring from point A to point B by doing this idea of sharing a signal line. So you'll see multiplexers and demultiplexers used quite a bit right there. Now, the book also goes through that we can also use a decoder as a multiplexer right there, where we're tying the data into the select line right there. So here's another circuit that we're going to use for a demultiplexer. It's actually not a demultiplexer, it's actually a decoder. We talked about decoders before, right? Right there. A decoder means that whatever input is selected here, S0 through 4, 3 in this particular case, that output is taken low, right there. But in order to use it as a demultiplexer, we tie our data in to our chip select NOT, right there. We ground our other one. This has 2 chip selects. This is the 74, 154, that there. And because we're tying this into a chip select NOT, and the output is inverted right there, we're looking at a DX that is converted out, that we're doing the double inversion. So whatever data is put into is then brought out on one of these, that particular output, and all the other ones are high, right there. So this does a disadvantage. It doesn't tri-state the unused ones, but it just takes them high. But it does work as a demultiplexer, right there. So now we're going to enter there, and I'm going to continue following this particular, even though I don't have slides for it. I had the slides for it, but they're up on the cloud, and I don't get internet in this room. That's right. I didn't copy the computer. Is parity. Now, parity is an important concept, and I'm just using the book here as kind of a guide to show me so I don't skip any topics there. But if I look at parity, right there, the idea of parity. This is what I want. Is that I've got a series of bits right here, 1, 1, 0, 1, for example, right here. And I want some type of error checking. I'm either saving these bits into a file, I'm sending them through a serial port, I'm sending them through some other, I'm storing in memory. But I want a very easy and quick way of seeing whether or not the data is correct, right there. And the easiest and cheapest way, not 100% there, but if you're talking a large amount of data, it's good enough, is we do what's called a parity check, right there. A parity check can mean we can have odd or even, right there. And what we do is we add another bit here, called the parity bit. Parity bit, right there. Right there, and we make that either a 1 or 0 to force the 9 bits to be either an odd or even number of ones. So if we're going to do odd parity, right here, we've got 1, 2, 3, 4, 5. I would make this a 0, right there. If I want even parity, it would be a 1. That's all parity. That's all parity is that we force our 8-bit number by using a 9th bit that is thrown away. We don't use it for anything other than error checking to ensure that we have either an even or odd number of ones in our number. And that way, as we go through, if there's an error, we can request that the data be resent, or that if you're talking a desktop computer, if you get a parity check error, you now know that you've got bad memory. That there's usually that's what used to cause a blue screen of death, and now there's other issues. But usually, if you get a parity check error, now some memory don't have parity, right there, right there. There's other ways of doing error checking. There's things called like a checksum, where you add up the number of ones, and that's stored as a large number at the end of the file. That's very commonly used if, say, for example, you're zipping a file or compressing it, or if you're sending it via some type of FTP site where it has a checksum at the end to verify the entire file is correct. But parity is one of the first easiest ways of doing error checking, right there. It's an error checking method. So as we look at our parity bit here, occurs, again, I don't want to necessarily read this, but basically it says errors occur as digital signals codes are transferred or stored. I'm going to throw in the note that they're stored. The concept of parity is basically sum of an even number of ones is always 0, and odd numbers is always 1, right there. That's basically looking at generate principle is used that you have either even or odd parity, and you force the odd bit right there. And the exclusive OR is normally the way that you would determine if you have odd parity. right there. And you just simply tie 4 of those together right there. The parity checker is a simple chip put out there, the 280. We're back to the mode of just explaining chips and their particular functions. That discussion on the multiplexer used for doing a Boolean table, that's a separate subject. The rest of this chapter is all basically explaining what they are. And again, a parity checker, all it does is it gives you an output signal, and you would know that as you look at, here's a complete circuit right here. Here we have our parity bit given right there. There's a receive on that end there. And this basically, I'm not going to go through the circuit. You don't need to memorize the circuit. You don't need to understand it, except for the fact that what we're doing here is we're transmitting data. There, our transmission line is there. We're demuxing it on the other end, and we have our parity checking device right there that looks at our data and determines whether or not there's been a parity error. This happens to be using odd parity right there. If we get even parity at the other end, then we've got a problem right there. And I think I'm losing my voice this morning. I feel something out there. That pretty much wraps up this chapter out there. We have another topic in this chapter. I'm going to switch books here and go into another topic out there. I'm going to revisit chapter 2 in Tochi. Well, actually not chapter 2, but it's chapter 2 in Floyd, and talk a little bit about negative numbers and that there. So as we look at this discussion there, I'm going to go back here and I need to right there. And I'm back to PowerPoints, which makes my life a little easier. That there, so that it looks like I. Right there. Okay. And let me put my keypad back on here. I don't think I got the little thing here, so I can hit the space bar. Right there. Okay. All right. We're going to be talking about subtraction, multiplication, and division of binary numbers. So we're into chapter 6 of back to the Tochi book. So as you can well guess, I pick and choose chapters out of books as the way that I like the way that the author he presents. So I don't like one book over another that well. So I tend to go back and forth. That's here. So I'm not going to there. Okay. Binary numbers are added like decimal numbers. We've talked about adding those numbers, so I'm going to kind of skip through that. We've already added binary numbers. That's not a problem. That's there. Whenever you add 1 to 1, you have a carry, right? So when we add numbers, if we add the numbers 0, 1, 1, 0 to 1, 0, 0, 1, that particular case we're going to get 1, 1, 1 up. 1, 1, 1. There's no carries. But if we add 1, 0, 0, 0 to 1, 0, 0, 1, we're going to end up with a 1, 0, 0, 0, and then a carry out right there over to the next digit. So now binary addition is subtraction, basically is the same thing as we would have to borrow. We really didn't do much in this subtraction. That's there. But again, when we represent signed numbers, we have to represent them in a separate way. And this is what we did not talk about very much when we talked about our binary numbers. We did not talk about negative numbers. Negative numbers use something called a 2's complement. That's there. And we have what's called a sign bit, which is our most significant bit. This particular number, they're showing a 7-digit number right there. Right there. So when we convert to that there, and I'm going to probably go off the one note here in a little bit, but a sign bit of 0 represents a negative number, or a positive number, a 1 represents a negative number. So we have the extra bit that there, and again, I don't know why he's using A6 instead of A7 there. Oh, the fans are probably on. Now that the air conditioner is working, it's probably a little chilly back there, right? Because I don't feel the fans up here. Up there. Besides, I grew up in the Midwest in the U.S. where it gets minus 40, so if this room got down to 12, I probably would be comfortable. That's there. You'd all be freezing together. All right, the 2's complement. That's there. So we need to know how to convert from a regular number to a 2's complement. And this is the way things are stored. Sooner or later you'll get the right. The speed controls are on the top there, I think. That there. So okay. Now, fortunately, Windows 10. I don't think Windows 7 or Windows 8 calculator handles 2's complements very well. The Windows 10 calculator does an excellent job of showing how to work with 2's complements, right there. But that there, 2's complements is a way of representing that there. And the way you normally do that is you just simply invert each bit and add a 1. That's the process. And it's the same process of going back and forth, right there. So, in other words, basically, first off, when we look at an 8-bit number, when we're dealing with unsigned, signed, it goes from 0 to 255, right? 2 to the 8th is 256. That's the number of numbers we have. So we go from 0 to 255. If we're dealing with signed numbers, we have to split that in half. And 0 ends up being treated as a positive number in this process. So when we're dealing with an 8-bit number that is signed, it goes from negative 128 to plus 127. So we have 128 negative numbers, 128 positive numbers, of which 0 is one of them, right there. And that's our range. If we're dealing with a 16-bit number, those ranges change. I'm only going to deal with 8-bit numbers for today's discussion, right there. So the process, if I want to represent, for example, a negative 56, right here, and I'm going to cheat. There's nothing wrong with cheating while I'm sitting in front of a group of people, because otherwise I make foolish mistakes, right there. Windows 10 has something called the calculator on it. Now, Windows 8 screwed the calculator up. Windows 7 had a pretty decent calculator, but the one in 10 is actually much better. That's it. So I'm just going to put the number 56 right there, and that's in binary. In hex, it's 38. So let me just deal with negative 38 hex right there. Right there. So how would I represent that? That there. So 38 is 0011 1000, right? I do the 2's complement of that. It's a 2-step process. I invert each bit 1 1 1 0 0 0 1 1. I add a 1 to it, and I end up with 1 0 0 0 1 1 0 0 right there. This happens to be negative 38 hex in 2's complement form. I know that it's negative because this bit is a 1. Anytime you see a 1 in the most significant bit, you know that the number is negative if you're dealing with signed numbers. And that's the same whether you're dealing with 16-bit numbers, 8-bit numbers, 32-bit numbers, or 64-bit numbers. Now, we're not talking about dealing with fractional numbers at this point. We're only dealing with plus or minus numbers that are integers right there. We're only dealing with that there. Now, if I go back to my calculator right here, right there, and I put in the number, first off, let's change this to a byte. right there. And this is the advantage of the Windows 8 calculator, or Windows 10 calculator. And I go into binary, and I put in the number, and it's 11001000 right there. Notice that my decimal shows as negative 56. That tells me that I did the process right. My hex is still showing up as unsigned, but at least it shows that I got the right decimal value, that it does represent as a negative number right there. Now if I convert it back, and I get that number and I convert it back, I repeat the same process right there. So I've got the number 11001000. If I want to see what that number is, I know it's negative, but it's a negative what? I repeat the process. 11101100. Add a 1. 0001. 1100, and I'm back to 38 negative right there. And of course that's in hex right there. So, and that's what I started with right here, was 38. So the process is fairly straightforward. Now, what gets tricky is that we're going to use this to do subtraction. And what we want to show is that if we add two numbers together, one is positive and one is negative, that we get the right answer by doing that there. The reason we do that is that computers, it's easier to build adders than it is to build subtractors right there. So when we go through this process right here, to change the number to the first change to the ones complement, you almost never hear the terms one complement, and then add 1 to the ones complement. There's a shortcut way of doing this. I almost hesitate to say the shortcut way, but the shortcut way, I'm going to say it anyway. The shortcut way is if you have the number, say 00111000, you start at the right, and every place there's a 0, you just write a 0, 0. And the first one you write, and then you start inverting right there. Notice if this is the first one, I don't invert that one, but then I invert everything to the left of the first one. That there, and that works perfectly fine then, right there. So you've got that particular way of doing it, but that's the way that you would convert back and forth between the two of them right there. A number is negated when it's converted to the opposite sign, and you find a binary number can be negated by taking the 2's complement of. So in other words, it's the same process of taking the 2's complement as going back from the 2's complement. It's the exact same technique. You just simply invert every bit and then add a 1 to the final result. If you've got a 16-bit number, it's the same process right there. So if I've got a 16-bit number that I want to find that they're 1101, 1100, 1100, 1111, right there. This happens to be a negative number. I don't know what it is. We'll find out what it is in a minute, right there. But again, I go through the same process, is that I'm going to invert each one of these. Add a 1, and I got 0010, 0011, 0011, 0001, right there. And that's the same thing. If I bring up my calculator, and I'm going to cheat a little bit here, where's my calculator, and put that on the same side, and I change this to a word, right there, and I put in that original number. Oh, what am I doing here? Let's clear. The original number was 1, 1. Oh, I'm not seeing that there. 1, 1, 0, 1. 1, 1, 0, 0. 1, 1, 0, 0. 1, 1, 1. So that number happens to be negative 9,009 is what that number happens to be right there. So if I put in 9009 right there, that number happens to be, should be the same as this number that I had, 0010, 0011, 0011, 0001. So you can see that we got the same number back. So again, the process is fairly straight up there. You can see now that the process is we just simply add the two numbers right there. So what I'm going to do is just do some examples here. Right there. And I'm going to stay with 8-bit numbers just simply because it's easier. 16-bit numbers, for a case of examples, it's messy. So let's just take, and we want to take the number 56 hex, and we want to subtract from it 38 hex right there. And I'm going to work in hex right there, simply because it's easier to work in hex right there. That way I don't have to go back and forth. But the result, so when we do this right here, what we're going to do is we're going to take the 2's complement of this number, and then we're going to add the 2 together. So the 2's complement of 0011, 1000 is going to be 1000, 0011. You know, and I did that using the cheaters method right there. So I'm going to add 0101, 0110, that's 56 hex, and I'm going to add to it 1100, 1000. We're going to add those two numbers together. Now, as it turns out, we're going to get a carry out that we're going to just simply ignore. So 0 plus 0 is what? 0, right? 1 plus 0 is 1. 1 plus, right there. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 1 is 0, carry a 1, 0, and a carry out that we ignore. Now, our result here is, it looks like, is 1E hex right there. Now, if we did this math here, we would have to borrow 16 from here, make that a 4. So we would have 16, and when we subtract 8 from 16, that's going to give me E, right? 16 minus 8 is 15. Excuse me. 16 minus, it's going, yeah, that's right. It's going to, right there, 16, right there. So if we pull up my calculator and cheat again, and we go to hex, and we take 56, and we subtract 38, our result is 1E. So we get the right result right there. So when we do the subtraction, we will end up with the right result right there. So it's an easier way of subtracting, because now we can very straightforward do, we just simply do the 2's complement. In a microprocessor, that's very simple to do right there. You just do a not and then add a 1 here, right there. Let me do another example where our result's going to end up being negative. Let's take 38 hex and minus 56 hex right there. Right there. So we're going to reverse that process, and our answer should be negative 1E. So 56 is 0101, 0110. The 2's complement of that is 0101, 0101. That's the 2's complement of that right there. As I said, I used the shortcut method to do that. You You may want to use the other method if you're doing this on the final exam. I've done the shortcut method so long that it's easy. Again, I just start at the right, and if it's a 0, I write down the first one I don't invert, and then everything else I invert moving forward. So I'm going to add 0, 0, 0, 1, 1, 1, 0, 0, 0, right there. And we're going to add to that 1, 0, 1, 0, 1, 0, 1, 0, right there. Boy, that comes out. Came out interesting, right there. So when we add that, we're going to get 0, 1, 0, 0, carry a 1, 0, carry a 1, 1, carry a 1, 1, and 1 here. Now notice that this number is negative. So if I'm going to go through here and find what that value is, I have to do the 2's complement of it, right? So doing the 2's complement of this number is 0, 1, 0, 1, 1, 1, 0, 0, 0. That looks a lot like 1e, right? Which is what we would expect our answer to be. So when we do negative numbers in binary, we find the 2's complement. When we add two numbers, one is negative, one is positive, if our result is positive, we'll end up with a 0 in the sign bit, a carry out that we ignore. If the result is negative, there will be no carry out, but there will be a 1 in the sign bit. Let me try writing that down in such a way that makes sense. So, to subtract. Take the 2's complement of the number below, in other words, the number you're subtracting from, right there, add the two numbers. If the result is positive, there will be a carry out that you ignore that carry out. If negative, no carry out, and a 1 for the sign bit. Right there. That's it. That's how we handle negative numbers. That there, when we add and subtract. Now multiplying is a little bit more tricky. We're not going to get into much dealing with multiplying and dividing. Right there. So, okay, let me go back to our book here. Or slides up there. Perform up there. The sign bits are added with magnitude bits. If the addition results in a carry out, the carry bit is ignored. If it's positive, it's in pure binary form. If it's negative, it's in 2's complement form. We saw that with that example already, right there. Subtraction used actually involves the operation of addition. That's what we just did. Number subtracted. The subtractend, which is the number name I could not remember. That's why I said the number below. That there. And besides, most of you probably have not seen that word subtractend, right? That's not a normal colloquial English that you find. That there. But that's the number that you're subtracting from the number down below is negated. When they say negated, it means you're finding the 2's complement of that number. The result is added to the minuend, or the top number. That's there. The answer represents the difference. It will be overflow will occur when two positive numbers or two negative results presents an incorrect result. Now, this is an interesting situation where if you're adding two negative numbers together and you end up with a number less than negative 128, or we're adding two positive numbers and the result is greater than 127, we have an overflow problem right there. And if you're dealing with microprocessors, it's fairly easy to catch that. If you're trying to do this with digital circuits, it's a little messy. The book shows some circuits for doing that. I'm not going to get into them in great detail right there. This kind of shows the table of going around using the circle right here. And what they're showing here is, as we go around here, that from here to here is positive, and this, we go to -8, we go all the way to -1 this way. So it does kind of a funky thing as we look around this table. Is here's our 0 point. As we go this way, we go -1 at a time, but as we cross here, we go from +7 to -8 right there. So apparent as we move counterclockwise at there, but again, as soon as we cross this boundary, we do a jump of 16 right there. So it just creates a problem with this overflow situation. Multiplication, I'm not going to spend much time on multiplication, but multiplication is basically an AND operation right there. The results are shifted, and all the results are added to final product. We do a shifting every time we move across right there, and there's an example right there. And I'm not going to go through binary division. We actually rarely do multiplication in digital logic. We will almost always use a microprocessor in that there. There are hardware multipliers. I've never built one out there. BCD. Now BCD is an issue right here. Is we've got the situation, and they do discuss BCD addition. BCD addition, let me kind of go through, is the fact that BCD numbers only represent 0 to 9. So if we have a result greater than 9, we know that's an invalid BCD number. And what we would normally do is just add a 6. We add and if we have a carry out, we have to add the 6 right there. So there again, hex additions that's again, we've done that already. So we've kind of gone through all these various ones. I think the only thing we really didn't get into much was we didn't get into the negative numbers. That's really what I had to come back and pick up at their end subtraction. This is the basic ALU. You'll see lots of that when you take your microprocessor course, so I'm not going to spend any time on that there. So we've got control, add a specific number. We go get the number from memory. We put it into the accumulator. We go get the next number. We put it in the B register, and then we do the add, and the results stored in the accumulator. That's there. And typically you will see the instructions are going to, at there, appears at each binary at there. I don't want to get into, we've talked about this circuit already, so I think I could pretty much wrap up. I think I'm going to end early today so I can have a little break before my next class. That there. And there's nothing I want to talk about in this. Parallel adders with registers, we're not going to get into that. That's more getting into the microprocessors right there. Because as we look at this here, because when you do a microprocessor, you're going to see something that says add a 35, and this 35 actually happens to be a memory location. So what the microprocessor does is it goes to memory location 35, grabs the data, adds it to the accumulator, stores the result in the accumulator. And they're getting into this discussion at this point, and it's a little, and we talked about the look-ahead adders. I think as I go through these slides, yeah, I'm going to stop at this point here. Get there. So I'm thinking in terms of labs, yeah, because the rest we're getting into VHDL. And I do need to come back and cover a little section on Verilog, introduction to Verilog or VHDL. I'll probably do a little section at the end on the introduction to VHDL. Actually, I may do that. I'll probably do that before I do finite state machines. My next discussion is finite state machines, so I think I'll do a short introduction next Tuesday on VHDL, and then we'll move into finite state machines. That's there. And then from there, we move into sequential circuits to wrap up the course. That's there. So Thursday, I'm still debating on whether or not I have to look at the calendar, see how many classes I got and how much material I've got. I may want to do a short little lab on Thursday on just doing the doing the 4-input multiplexer circuit that I talked about at the beginning of class today. I'll write up a short little. Yeah, the lab would be basically, we'd have our ABC truth table here, and we'd have our inputs here, and you would just simply verify that we got the truth table. It would be a relatively quick lab. So what I would probably do is do the lab at the beginning and then do a quick introduction to VHDL while you're at the computers so that you can follow me along and do a short little VHDL lab up there. And the reason I want to do a short little VHDL lab is because it's easier to explain finite state machines using a high-level language versus trying to do counters using, as I look at some of the previous finals, they had you doing sequential circuits, doing K-maps and designing counters, and I'm not going to make you do that. Nobody does it that way anymore. They almost always use a high-level language for counters anymore. So I think I'm going to use VHDL mainly because the books both use VHDL. I know VHDL very well. I think Sheffield, when you get there, if you take the advanced course, they'll probably shift you to, are you going to Sheffield or is that the university? You don't know what university you're going to. Whatever university you go to may shift you to Verilog. Verilog and VHDL are very similar languages. That they're a little bit different. VHDL is much more common in the U.S. than it is in the rest of the world. It's also very common in Europe. Verilog is more common in Asia. And Australia and New Zealand tend to follow a little bit more of what Asia. And Verilog is a little bit more common in commercial applications versus military applications. So Verilog is most likely what you would use if you were to do design work here in Malaysia. So I'm being real honest that I'm teaching you the wrong language that you would use here. But because we have no books that are written at the level that you need for Verilog, I found several books. I looked at them, and they're way beyond what you guys are ready for. They're written very cryptic. I even had trouble following a couple of them. And so these books both have an introduction to VHDL in the book. We've been using the books. They're written at the right level, so I'm going to use Verilog or VHDL. I've used Verilog in the past, but I'm far, far, far more familiar with VHDL. So Thursday, I'm still questioning whether or not I'd like to do another lab just simply because I like to see. I think you like to get in the lab and see things happen, right? And it's better than listen to me talk for 2 hours or an hour and a half each time. So I'd like to do that, but I also can't give up the entire 2 hours. So I'm thinking about doing a 1 hour lab, short lab, and then let me talk for the last hour. Is what I'm thinking. So Thursday would probably be a full 2 hour session. Because we start at 12 o'clock, right, on Thursday? Yeah, because I have a class before that on Thursday. So I could start right at the 12:15 and run all the way up. And if we run a little bit long, that's fine. So, all right, I'm going to quit here at this point because I've got another 2 hours of talk. My voice is giving out already. Actually, I've got 2 hours of talk right after this class, and then I got another class this afternoon. So I still talked almost my full normal hour and 15 minutes, right?